Also, we have another doubt session again this week. So especially any doubts from the module or the worksheets that I've sent or HC Verma in kinematics, Newton's laws, whatever, we'll discuss. So the equations of relative motion, we had discussed the general equations in vector algebra last time. So today is very important lecture because we'll be seeing number of applications of that. So we had seen that the position of one body with respect to another, let's say for B with respect to A, is the position in the absolute frame minus the position of A in that absolute frame. So from this we get displacement. Relative displacement is displacement of B in the ground frame or absolute frame minus displacement of A in the ground frame. Velocity is a similar equation, and acceleration has a similar equation. And we will understand through some examples today that the third equation that we're writing, the relative acceleration one, or the fourth equation, whatever, this can also be used to explain the concept of pseudo force, which you have been studying in Newton's laws of motion. So let's begin with an example. So we have this situation that there is an elevator which is moving vertically upwards with an acceleration of T0. Okay. And the height of the elevator says h. Now, there's a person inside the elevator, and what he observes is that there is a screw or a bolt, whatever, let's say B, which comes off the ceiling and eventually comes and hits the floor. So a bolt B on the ceiling comes off and falls to the floor. Okay, so if h is equal to, let's say, 6 meters, it's an extremely tall elevator, let's say it's a freight elevator or something. So 6 meter height is there. Okay. So the first part of the question we'll see is that if the observer finds that the time of free fall inside the elevator for the bolt was 1 second, then find T0 and what is the time of free fall as observed from the ground frame. Okay, so try this question out. So interestingly, you can actually solve this question also by using Newton's laws and pseudo force concept. But here we will solve it using relative motion concept. We'll discuss the second part of the question also, but first let's work out the first part. Okay. Yes, very good. Anirudh and Arnav, your answers are correct. And Janvi, your answer is correct also. What about the acceleration?
So which acceleration?
The acceleration of the elevator, you have to find A0.
That is the answer.
Anirudh and Arnav, your answer is correct. Okay, Janvi,
Acha, sir, I took it the height to be 16 meter. Just a second.
Oh, 6 is this thing. Actually, I thought 6 is the answer you gave for time.
No, sir, no, sir.
So time should be same, right?
Time should be same. That's correct. Very good. Okay. Okay, so let's solve this question by using relative motion concept first. Okay. Then we can also solve it by using that what's happening in the ground frame. But easiest and most natural way of solving this would be for the observer inside the elevator. In his frame, what is happening? Okay. So the elevator is going up with an acceleration a0. So whereas as the bolt falls, so let's say t equal to 0, the bolt is here, and as it falls, at any time t, it is having a motion like this. So acceleration of the bolt in the ground frame is minus g j cap, okay, because it's in free fall. The only force acting on it is gravity, okay, but acceleration of the elevator is plus a naught j cap. So acceleration of the bolt in the frame of the elevator is going to become minus of g plus a naught j cap. So in simple terms, we can say acceleration of the bolt with respect to the elevator is g plus a naught downwards. So what this fellow will observe is that it's coming down with this kind of an acceleration. And it hits the floor at a time of capital T, let's say, which is 2 seconds. Sorry, 1 second, right? I've given the answer is 1 second. Okay. So this is one important thing. The other thing which is important here is what is the initial velocity of the bolt with respect to the elevator. It's stuck to the ceiling, and it's starting from, so this is 0. So this is important. Okay. So from this you can see that the displacement of the bolt with respect to the elevator as a function of time vectorially, it will be minus half g plus a naught t square j cap, or we can just say that it is half g plus a naught t square downwards. So now this is the thing which will give you the answer for this. Okay, that this is going to be h at the time t. So 6 is going to be half of 10 plus a naught into 1 square. So you can see from here this a naught will come out to be 2 meters per second square. So this is the most natural way of solving this. Okay, the most intuitive way, that when you are standing inside the elevator, you see that the bolt is falling to a height of h, but its free fall acceleration will be different for you. It will not be equal to g, it will be g plus a naught, because you yourself, along with the floor of the elevator, are part of the non-inertial frame or the accelerated frame. So relative motion equation will apply.
So if the particles are moving at very large speeds, then the time should be different from the observer inside than outside. Huh?
Yeah, especially if the elevator is moving at a very high speed, but then that is like relativistic speed which is comparable to the speed of light. Then there is that phenomena called time dilation, right?
Yes, sir.
Which happens in special theory of relativity, that for any event, the time of that event or the time period of that event is different in different moving frames. Okay, anybody tried any other method?
No, sir, I just took it that the bolt is going to fall with G, but for the for the floor of the lift and for the man, it will who are moving up with A naught, it will seem like it's following with A plus A naught plus G. So that's all I did.
Okay. But then, so you solved it in the ground frame, right?
No, sir, for the floor I solved.
Yeah, but basically you're seeing the floor moving upwards at A naught.
No,
So
sir,
that means you're...
for the man I solved. So the man on the floor of the lift.
But man on the floor of the lift does not observe the floor moving. Na? For him, the floor is at rest. Understanding? Na? So you are then solved in the elevator's frame only. Na?
Yes, sir, in the elevator's frame only I solved.
So in the elevator's frame, the acceleration of the bolt will not be G. Na? It will be G plus A.
Yes, sir, G plus A.
Downwards.
Yes, sir.
Right. Okay. Now a couple of more methods we can use to solve this. Okay. In fact, let me actually give the second part of the question also. Then we'll come back to solving it by another method. The second part of the question is that B. If the elevator has a velocity of 4 meters per second upwards at the instant the bolt drops or comes off, okay, then find the distance traveled by the bolt.
Sir, in the A part, for a person on the ground, it will not seem like the bolt has traveled 6 meters, right?
No, it will not seem like. Okay. So keeping this thing in mind also, but let's first solve it for the A part only, but by looking at it from ground frame point of view. So from ground frame point of view, what is happening is that at t equal to 0, the bolt is here, okay, and the elevator is here going up with an acceleration and with some initial velocity, which in the second part is given to us, but let's say here is unknown. And then at 1 second, what happens is something like this. The bolt has reached here. And the elevator has traveled like this. So for the observer on the ground, what is happening? The initial velocity of the bolt in the ground frame is uj cap, which we don't know. Okay. But the acceleration of the bolt is minus g j cap. And the initial velocity of the elevator is the same thing, but unknown, let's say. You can also substitute the value given in the second part, but you'll see it's not necessary actually. Acceleration of the elevator is a naught j cap. So from t equal to 0 to capital T equal to 1 second, the displacement of the bolt will be how much? It will be ut minus half gt square j cap, and the displacement of the elevator will be ut plus half a naught t square j cap. Okay. So we can see basically that if we write this as a scalar, it is half gt square minus ut downwards, okay, and this is ut plus half a naught t square upwards. Now, you can see from the diagram that the sum of the magnitudes of these two displacements should be equal to h. At t equal to capital T. So the sum of these two displacements is to get that same relation. But as far as the path of the bolt is concerned, it's a little bit more complicated. In the ground frame, the bolt will be seen actually first going up and then coming down, because it has some upward initial velocity, which is what we'll require in the B part also. Now, this might seem very odd that how come the bolt is going up and then coming down, whereas in the elevator's frame, we see it only coming down. Is because while the bolt is going up and coming down, the floor of the elevator is also going up and coming down. But remember, the elevator is traveling in the upward direction at a faster rate. So, you know, what happens is, like, let's say the bolt comes off at this moment. So next moment, you see the elevator is somewhere here. And the bolt is somewhere here. In the frame of the elevator, the bolt has still actually come down. Okay. Next moment, we see that the elevator is somewhere here. The bolt is, let's say, somewhere here. Then eventually we see the bolt starting to fall. Now the bolt is somewhere here. This kind of series of events happens.
So for the man on the ground, the bolt is falling with 10 meters per second square, right?
Yes, at G. It's in free fall. Now, this thing that, you know, for the man on the ground, it is 10, but for the man on the elevator's floor, it is 12 or whatever, G plus A naught. We can also justify this by making a free body diagram of the bolt while it is in free fall in each of the frames. In the ground frame, in your FPT, there will be only the single force of gravity acting on it. So its acceleration should be only acceleration due to gravity. But in the elevator's frame, as you know, you'll have to include the pseudo force. So the net force acting on the bolt during the free fall in the elevator's frame, that is a non-inertial frame, will be the vector sum of pseudo force and mg. So that will provide the acceleration, which you will see will become g plus a naught downwards. So actually, the order of logic in that is the other way around. The pseudo force concept is justified by relative motion.
Okay, sir.
So hope the second method is clear. You can now work out the second part of the question, where the initial velocity of the elevator at the moment it starts going up, I mean, at the moment the bolt comes off, is given to you to be 4 meters per second. In the B part, u is equal to 4 meters per second upwards at t equal to 0 when the bolt comes off. So you have to find the distance traveled.
So the elevator is still going with acceleration A naught.
Yes, the elevator has constant acceleration.
Yes.
That is like what we've assumed from the beginning for A part also. So before we solve the B part, another interesting thing here is you can see that from this data, you'll also be able to understand that the taking u to be 4 meters per second upwards, the displacement of the bolt in the ground frame will become half into 10 into 1 minus 4 into 1. It's actually only 1 meter downwards. And the displacement of the elevator during that time is ut plus half gt square. Oh, sorry, plus half et square. So you can see it is 5 meters upwards. And therefore you can see that
Then, sir, what is
but
the
these
distance traveled?
These are the displacements. Okay, this is not the distance, these are the displacements. So for the distance now, just pay attention to the diagram where I've showed you the actual trajectory of the bolt. It doesn't come straight away down now. The bolt has an initial velocity which is upwards now.
Yes, sir.
Okay. The distance traveled by the elevator's floor will be this much only because it has only a upward motion. It doesn't go upward and then come downward or something. Okay, but the bolt's trajectory is such that initially it is in ascent and then it's in descent. So you realize that the distance can only be calculated by understanding the motion of the bolt from the ground frame point of view. Because in the elevator's frame, the bolt is never going up and coming down. It's just straight away coming down.
So the sum of this upward and downward, the entire distance covered in this upward downward is actually equal to 6 meters only, no?
No, I mean, it might come out by as a coincidence, but it doesn't have to. To understand now? Because that's nothing to do with this now. It
Sir,
depends on the initial velocity. It depends on the initial velocity. No? Suppose the initial velocity was 2 instead of 4, it would be something else. No? But the time would have been the same, the displacement would have been the same, the relative acceleration would have been the same. So this is where it is at t equal to 0. Okay. So in the ground frame, when we are seeing it, it has an initial velocity of, we are saying 4 meters per second, and it has an acceleration of g downwards. Okay. So it goes up and eventually hits the floor. So you can see that from here to here, this, if I write this as capital H, that is how much? U square by 2g. So it is 4 square by 2 into 10. So it is 1.6 meters. So 0.8 meters. So the total distance traveled will be equal to h plus h plus this. This had come out to be how much in the last part we had seen? will come out to be 1 meter, right? It's traveling 2.6 meters. So my diagram is like not proportionately drawn. This SC should be more, this SP should be less. Okay. So the actual thing is more like this. This is the situation at t equal to 0. Then by the time the bolt hits the floor, it's the floor that has done a displacement of 5 meters. So this is displacement of the bolt. But the actual trajectory of the bolt has been like this. So in the time that the bolt has actually ascended 0.8 meters and then descended a total of 0.8 plus 1 or 1.8 meters, the floor of the elevator has come up by 5 meters to come and meet it. But throughout that time, for the person standing inside the elevator, it look like the bolt is always coming down. Because even while the bolt is ascending, the elevator is itself ascending at a faster rate. No? So in the frame of the elevator, it's always coming down. I hope that point is clear to all of you here.
So can you go up little? Up.
Yeah.
Yes, sir.
So this is A part solved in the ground frame, right? You want to see this or the non-inertial, I mean the
This one
relative
only.
motion? This one. Okay.
Sir, done. Yeah.
Okay, so hope this distance part is particularly clear to all of you. This is like a more tricky part of the question. So another way to understand this question nicely is that if you look at the velocity time graph of each of these within the same thing, if we superimpose for that 1 second time or whatever, this is, let's say, a velocity versus time graph where we are using the convention that upward is the positive axis. Okay. So for the bolt, what is the velocity time graph going to look like? It's like a regular free fall thing. No? So it's initial velocity is positive and it starts falling at the rate of g. So for the bolt, it's like this, that it is +4 initially and its acceleration is -10, the ground frame. So .4 seconds and so 1 second is here. So at 1 second, the velocity would have become minus 6, right? But in the same thing, if we superimpose the velocity of the elevator as a function of time, we will see it's like this. The elevator is having an acceleration of plus 2. So you can see that this relative motion is always increasing with time at any instant. So the velocity of the bolt with respect to the elevator, we write with proper sign convention. It is always minus 12t j cap. So the motion of the bolt in the elevator's frame is always downwards. So in the same thing, if you look at the relative motion of the bolt with respect to the elevator, that will look like a graph like this. This is the bolt relative to the elevator. That is the difference of these two graphs.
Sir, but sir, velocity of the bolt with respect to the elevator will be 0 at some time before the motion was recorded, right? At t is equal to 0.
Even when the motion starts at t equal to 0, because at that moment it's just coming off the ceiling, no?
Yes, sir. But sir, according to our formula, it should be -4 as soon as the motion starts.
But that formula is not applicable before the bolt comes off, no? Because it's not in free fall before the bolt starts off.
Okay, sir.
You're understanding, no? This formula that we've written for the velocity of the bolt, that is only applicable from our t equal to 0. And that is the instant when the bolt starts falling. So before that, the bolt and the elevator have a common motion, no? Because the bolt is attached to the elevator ceiling.
So, but isn't RT is equal to 0 and the graphs 0 same the same?
Exactly, no? So that's why it is applicable only from 0 onwards, no? It's not applicable from before 0. So the only graph that will continue over here is the elevators one. Okay, the bolt and the relative motion graph, that is only limited from 0 to 1 second. Because at 0, the bolt starts falling, and at 0, it hits the floor. Oh, sorry, at 1 second, it hits the floor. Is it clear now, Janvi?
Sir, I'll write it down. I'll get it if I write it down.
Your question is for what is happening before t equal to 0, no?
No, sir. Sir, it's simply the formula. Sir, if we put t is equal to 0 in the formula, we get -4. Sir, velocity of bolt with respect.
In which formula?
Sir, velocity of bolt with respect to elevator, we've written -12t -4, right?
No, we have not written. See, beta, it's just -12t. Actually, see, you have to convert this to a vector before you write relative, no? So the bolt's velocity as a vector is 4 minus 10t minus j cap, no? And the velocity of the elevator is 4 plus 2t plus j cap, no? So when you subtract these two,
12.
the 4 and
There
4
is 12.
cancel out. Just only 12.
Okay.
12 downwards. So this formula is limited only from 0 to capital T equal to 1 second. Because this formula is only limited from 0 to 1 second. The elevator's motion is continuing in the same way after 1 second also. But these two. So that's what I've shown in the graph also, that this graph will continue in this way as long as the elevator is accelerating upwards. But the bolt's motion thereafter will change.
So can you show the B part?
Sure. So B part, we are calculating the distance traveled. Okay, so this is the A part.
Yes, done.
Okay, so this is the distance traveled by the bolt, but specifically from t equal to 0 to t equal to 1 second. Okay, because even after 1 second, the bolt continues to travel, so its distance will change. Okay, but only for that time when it was dropping off inside the elevator. It was in fall inside the elevator. After 1 second, here we are not concerned with what happens because the bolt might actually bounce off the floor, or it might just get stuck to the floor. So accordingly, its motion will be. Okay, so now just a note about the concept of pseudo force over here, that in a non-inertial frame, that is an accelerated frame. So though you know this, but we'll see the logic of this from relative motion point of view, application of Newton's second law. So in ground frame or inertial frame, okay, we say that the net external force acting on a rigid body is equal to mass into acceleration, okay, which actually comes from the fact that the net external force is equal to rate of change of momentum. And here we are assuming that mass is constant. So then rate of change of momentum will become m into a. Now, if we look in the relative motion concept, the acceleration of a body with respect to a non-inertial frame will be equal to the acceleration of the body, okay, minus the acceleration of the non-inertial. So in this above equation, the acceleration of the body in the inertial. So this thing here, we are writing as, okay. So now this equation can be written like this, that A is equal to acceleration of the body in the non-inertial frame plus acceleration of the non-inertial, or it is the relative acceleration plus acceleration of the non-inertial. So now from the above equation, we have m into A so m into A is F net. This is the net external force So in this equation now, this is the net force. Okay. But this is the acceleration of the body as seen relative to the non-inertial. So basically, this is mass into acceleration in the non-inertial. So the above equation converts like this, that F net plus pseudo force is equal to mass into acceleration as seen in the non-inertial. So this becomes the equivalent of Newton's second law in the non-inertial. Where comparing with the above equation, you can see that okay, ultimately this equation only, this is converted to this. This equation is converted to this. So you can see that pseudo force is equal to minus of m into acceleration of the non-inertial. So from that perspective, if we were looking at this, what the observer inside the elevator would say is that on this body as it is in free fall, because he is become a non-inertial frame, which is traveling with an acceleration a naught upwards. So there's a combination of mg and pseudo force. So the acceleration that he sees for the bolt with respect to the elevator, that will be like this, that mg plus ma naught, which is the pseudo force, is equal to mass into that relative acceleration. So acceleration of the bolt with respect to the elevator is g plus a naught. So though in this particular question, we are seeing this in 1D context, but this now applies in a general three-dimensional situation. If you see the equations which I've written on the left-hand side, they are generalized equations for three-dimensional vectors, general 3D vectors. So you can see that the statement of Newton's second law in a non-inertial frame, that the net external force or the sum of all forces acting plus an pseudo force equals to mass into acceleration in the non-inertial frame, where the acceleration that we're talking about is the acceleration relative to the non-inertial frame. So that statement is just another way of expressing the concept of relative acceleration. Okay, people. So hope this gives you a fresh insight into the concept of pseudo force also. Okay. Of
Yes,
course,
sir.
if you have read from Resnick Halliday, you have realized this is how they've explained pseudo force also. Okay. But you might not have understood this before because you have not done relative acceleration before studying pseudo force. Okay. So now I hope it makes it all clear. So in case you were finding the concept of pseudo force a little awkward initially, now this will make more sense into it. All right, now let's move on to a two-dimensional example of relative motion. We'll see very interesting example of relative motion from 2D point of view. Okay, so we have this type of a situation. We have, let's say, an intersection of two perpendicular roads, which we are seeing from an aerial view or top view. Okay. So it's like a regular perpendicular intersection of two roads. Now we have two cars that are simultaneously moving towards the intersection. So let's say A and B are two cars like this. Now A is moving with a uniform velocity of let's say 16 meters per second, and B is moving at the same time with a uniform velocity but of 12 meters per second towards this intersection. And at this given instant, which is t equal to 0 on my clock, let's say, both of them are equidistant from this point, where the intersection meets, when where the two roads intersect. Both are equidistant. So A and B move uniformly as shown, and at t equal to 0 are at a distance of, let's say, 50 meters each from the intersection O. So first of all, show that they do not collide, which is obvious because they have different speeds. Okay. Second, find the velocity of B with respect to A and the velocity of A with respect to B, taking the XY frame like this. Taking a reference frame like this, that x-axis is along the direction of A's motion and y-axis is along the direction of B's motion. And third is going to be the very interesting part, that find the closest distance between A and B. Okay. And the time at which the distance occurs. Okay. What is the closest that they come to each other, and at what point of time they come closest to each other? Now, there are various ways of doing this third part. You can convert it into an interesting calculus problem, looking at it in ground frame point of view. But one very interesting solution of this will be from the relative motion point of view, which we will discuss in detail over here. But first of all, I want all of you to get the answer to the second part correct, okay? And understand that answer, interpret that answer properly, that what we mean by this relative velocity, when we get it as a vector quantity, when you observe what its magnitude and its direction is, how you will interpret that. That's very important over here. Yes, very good. Anirudh, Arnav. Arnav, I'll just check that answer. 10 root 2 according to you. No?
Yes, sir.
Okay, so taking this as our reference frame, so this is our x-axis and this is our y-axis, suppose. So you can see that in ground frame, the uniform velocity, they do not collide. We can see that very easily because you can see that A reaches the intersection at TA equal to 50/16 seconds and B reaches the intersection at TB equal to 50/12 seconds. So they don't reach simultaneously. So they do not collide.
Sir, or we
That's
can
it.
just
Yeah,
we
sorry.
can subtract the velocities of this vectorially and
Yeah.
show that the relative velocity does not reach the point A. When
Yes, very good. Very good. That is also a very nice method of showing that they do not collide. And actually that will be an easy method of solving the third part also. That the relative velocity does not cut A. The relative velocity of B with respect to A does not go through the point A. But as it goes past A, there is some point where it reaches closest, no? Right?
Yes, sir.
So let's first work this out. So VA in ground frame is 16 I cap. VB in ground frame is 12 J cap. So naturally V of B with respect to A will be minus 16 I cap plus 12 J cap. And V of A with respect to B will be opposite to that. It will be 16 I cap minus 12 J cap. Okay. Now let us understand the interpretation of this. Okay. That's the interesting thing. So if we look at this thing from three perspectives, one is from the ground frame perspective. The ground frame observer is seeing A move like this. He's seeing the intersection point as stationary. And he's seeing B move like this. Okay. So after some time, he would have seen that A has reached somewhere over here. B has reached somewhere over here. So A has traveled by a distance of 16t. Like this. B has during that same time traveled by a distance of 12t. Like this at time t. This is one perspective. Okay. Now another perspective is like, let's say my observer is inside A. So then what this guy is seeing is something very interesting. He is seeing that this point O is actually moving towards with. The intersection point is actually moving towards him at minus 16 I cap. And what he's also observing is that the point B or the car B, which is initially over here, this is moving in this sort of direction. So it's more like going to be this sort of direction. Try and get this a little more.
Sir, I didn't understand this line.
I'll explain. Okay. this is the velocity of B as seen by A. Now. It is minus 16 I cap plus 12 j cap. So what the observer A will see is that at some time t, he is where he is now. He is not moved. In his own frame, the car A has remained where it is now because he is sitting inside it. But at that time, this point would have come closer. Okay, and the car B would be now looking like this at that time. You're understanding? Now compare these two diagrams and it will start making sense to you. See, if you're observing this from the ground, you're seeing A and B both moving towards a stationary point, which is the intersection point O. But if you're sitting inside the car A, how it looks? It actually looks like the opposite of that, that the point O is coming towards you. And the point B is moving in this diagonal sort of manner because the car is stationary with respect to you. You're understanding, no?
Yes, sir.
Okay. So for example, for this observer, when he's over here, what is the relative position of B? It's like this now. Both the X and Y coordinate of B have decreased.
Yes, sir.
Though actually in the ground frame, what has happened? Only B's Y coordinate has changed, but A's X coordinate has changed. Okay. So similarly, now if you observe what is happening in B's frame. Okay. In B's frame, now it's like this. The intersection point is moving downwards towards him, and the car A is moving in some direction like this. The intersection point is moving like this with respect to it. It is having a minus 12 j cap kind of velocity. Okay. And the car A is having a velocity which has 16 I cap component and 12 j cap component. So it's moving in a direction like this. So at some time t, what this observer will see is that the car A has come somewhere here. And this intersection point has come somewhere. This is in A's frame. And this is in ground frame. Okay. So hope this vector relation is now making sense. Why this relative velocity is like this. V of B with respect to A. So this is a vector of magnitude 20 meters per second in a direction like this, where you see that this angle becomes 37. And this one, velocity of A with respect to B, 16 I cap minus 12 j cap in meters per second. This also has the same magnitude, but opposite direction. It's like this. This angle is 37 degrees. Okay, so now this part is not only going to, not only we found out the relative motion, but this gives us a very intuitive way of finding that minimum distance thing. It's now a geometry problem. So, in A's frame, the car B is just moving along this dotted red line. So at some point of time, it must come closest now. So we should be able to calculate that geometrically. Okay, so we see. So now I'm just looking at the geometry of this more carefully. So I'll try to draw a more accurate kind of diagram. Okay, so at t equal to 0, say A is here. From the intersection point O at a distance of 50 meters. And at that point of time, B is also equidistant at a distance of 50 meters. Now let's say I'm observing this from A's frame. So my observer is here. So as discussed, this would move along a line like this.
Then the shortest distance is perpendicular. No?
Yes, we'll have to drop the perpendicular. We'll have to understand this geometry. Okay. So B is moving along this line with respect to A, and this line is along this vector VBA, okay, which is 20 meters per second in magnitude, but this angle is 37 degrees. Okay. So when it comes closest, that is when it's over here. This is when the distance between them is minimum at this point of time. So B is here at what time we have to calculate, and what is this minimum distance we have to calculate. Okay. So do you know that formula of equation of straight line distance from a given point, perpendicular distance from a straight line? Can you use
No.
that also? Okay, so it's okay. You'll learn that later in coordinate geometry. So right now, let's just solve it like this. I draw another line here. So I can see this is 50√2 is the hypotenuse of this triangle, right? And
Yes.
now what would this angle be here? This one. This angle theta would be 53 degrees minus 45. Correct?
Yes, sir.
So what is D minimum now in that trigonometry of this triangle, because this is a right angle triangle. So this minimum distance is 50√2 sine theta. So it is 50√2 sine of 53 minus 45. So sine of 8 degrees, but we'll calculate sine of 8 degrees using this. But we'll use this formula only to calculate it. So it is 50√2 sine 53 cos 45 minus cos 53 sine 45. This will be the easier way of calculating it. So 50√2 into 4/5 into 1/√2. Ultimately, you see it's not a tedious calculation. It's quite a simple calculation. So 50√2 into, take the 1/√2 outside, Take the 1 by 5 also outside. You're left with 4 minus 3. The answer is very simple actually, it's 10 meters. So the closest they come to is 10 meters. And another thing you will see, we can calculate the time by using the fact that if this distance S of B with respect to A in that much time. So from the triangle again, you can see that S of B with respect to A is going to be 50 root 2 cos theta. So I'm just doing this calculation directly. Cos A cos B, so that will become 3 by 5 into 1 by root 2 plus sin A sin B, so 4 by 5 into 1 by root 2. So this will actually become 8 into 10, 80 meters. Just check my calculation data. Okay. So now this distance should be equal to the magnitude of the relative velocity into time. So this will become 80 by 24 seconds. So it will come to the closest point at t equal to 4 seconds. As you can see, there's a very efficient and easy way to understand the question also, because see, the thing is now you're looking at two moving objects and you're trying to understand when they come closest. But if you work in a way that one of the moving objects becomes stationary for you, then the problem is that much simpler. No? You're seeing only the other object moving. So it's easy to find out when it comes closest. So that's what we're doing in the relative motion concept. Instead of looking at A and B moving separately in the ground frame, we are getting into a frame where A is stationary, that is A's frame. And we're looking at the motion of B sitting at A. So it's very easy to find out when B is coming closest, okay, what time it is coming closest and all that.
So after we found D minimum, what did we do after that?
I wanted to find the time at which it comes closest.
Yes.
So for that, I found the other side of that triangle, the base, you can say. So that is the actual displacement of B with respect to A. Na?
Yes.
And the displacement here should be velocity into time because there's no acceleration.
Okay.
So to calculate time, I have done that. I have calculated that base to be 80 meters. So in A's frame, B has traveled 80 meters in that much time when it's come to the closest point.
Yes, okay.
So this is, in this method, we are using this B's motion relative to E. So another thing you'll see here is that actually it's like, B has gone past A. So coming back to ground frame, this will be at a time when A has gone past the intersection point. So you can observe that also because the time is coming out to be 4 seconds. So in 4 seconds, A would have traveled how much? 16 into 4, 64 meters. So in the ground frame, A has actually gone past the intersection point. So you can also convert this to a calculus problem. What you can do is you can observe this from the ground frame and write the coordinate of A and B as a function of time with respect to our fixed XY system with O as the origin. And then you can use distance formula. So you'll get the distance between them as a function of time. And then you can use maxima minima concept. Even that will not be too difficult because you'll get it as a quadratic function. So it's not too difficult to find the minima of a quadratic function. Okay, so that other method I was telling you about, let's discuss that quickly. So you're seeing this in the ground frame. So at t equal to 0, A is here. Its coordinate is, if you take this as x and y axis like this. So A's coordinate at t equal to 0 is minus 50, 0. And B's coordinate is 0, minus 50 at t equal to 0. And they are moving with uniform velocity 16 meters per second and 12 meters per second like this. So therefore, at some time t, I can see A's coordinate will become minus of 50 plus 16t x coordinate, and it's always moving along the x-axis. So y coordinate is 0. And at that same time t, B's coordinate will have become 0, minus of 50 plus 12t. Okay. So the distance between them as a function of time, I write this distance formula as capital D. So the distance between them as a function of time is so it is 16 square plus 12 square t square. Okay, minus 100 into 16 plus 12 t plus twice of 50 square. So that will become how much? So this t is something like this. 20 square t square, okay, minus 2800 t plus 5000. So for the minima, we just need to calculate this whole quantity's minima. Just think of this like a function of time. So to begin with, you can see that so we are getting the time as something else. Something might have gone wrong in our calculation. We just check.
But in the previous method, the calculation was wrong.
In the previous one, the calculation was wrong, is it?
Yeah, it was not 80, it was
Which part, Beta?
70.
Oh, okay. This, right, my mistake. Okay. This is 70 meters, so this will come out to be 3.5 seconds, correct? Yeah, let's just correct this. So this is 50 root 2 into 1 by 5 root 2. I'm taking common, and 3 plus 4. Yes, by mistake. So it is going to be 70 meters. So the time is 70 by 20 because the speed is 20. Okay, so please note this correction, people, in the previous part. concept was correct, just one calculation mistake with that. So okay, so anyhow, so when we work this out now, we'll see that the distance between them as a function of time, it's going to work out something like this. First decrease and then again increase. So initially it was 50 root 2, and it come to some minimum value, which we'll calculate in a moment. But the time at which it will come to that minimum value will be 3.5 seconds. And that D minimum should, according to the above equation, come out to be 70 meters, which we can show in a moment from here. Okay, so F prime is this, 0 means that here T is so that is 3.5 seconds, and therefore this D minimum will work out to be 400 into 7 by 2, I'll write it like this, square, minus 2800 into 7 by 2 plus 5000. So when we work this out, this should come out to be 70. It will come out now, I think, because we got the time correct. So from this value of time, you can also understand that this minimum distance is going to actually occur at some time when A has gone past and B is somewhere here. No, not now. Okay. Sorry, because the time is now 3.5. So for example, 12 into 3.5 is how much? 36 plus 6, 42. So B hasn't reached here yet. So the minimum case will be somewhere here. When B is somewhere here and A is where at 16 into 3.5. So 48 plus 8. So 52. So A has gone past it. So A is somewhere here. This is when the distance between them becomes better. A has gone past, but B has not yet reached the intersection point. So this D minimum was not 70. It was how much? It was 10. No? Yeah. So you see that at the moment when this happens, A's coordinate will be 6, 0 and B's coordinate will be 0, minus 8. Okay. Anyhow, so hope the solution is fully clear, people. Okay. So here we have used this trick that distance is square root of some function of time. So distance is square root of this function of time. So when distance is minimum, inside the square root, the function has to be minimum. So instead of dealing with the whole square root term, we just deal with this function inside the square root. So that function is this. We just need to calculate its minima. This minima we'll see will be 100. So this whole term will become square root of 100. So it's okay. So now we look at another example of relative motion. Relative velocity of falling raindrops with respect to a moving observer. So now first example, let's assume that rain is falling vertically. We'll also take a later example where rain might be falling at a slant because of wind. So this is the velocity of raindrops with respect to the ground plane. Whereas, let's say a person is moving along the ground. So to the moving person, the rain will appear to fall at a slant. Because what will happen is his velocity vector is like this. So the rain's vertical velocity is like this, let's say. So the relative velocity of the rain with respect to him will become this vector. And it will be falling at a slant angle theta like this. So to this man who is himself moving like this, the rain will appear to fall in this sort of direction. So from the vector diagram, you can see the magnitude of this. It just becomes square root of the sum of the squares of the ground frame velocities, and the angle at which it appears to fall will be tan inverse of the man's speed in the ground frame divided by the range speed. So the faster the person is moving, okay, the more slanted the rain appears to be, and also the faster the rain appears to be.
So if the rain initially is also in a slanting manner,
then we'll have to recalculate this formula, okay, because they will not be perpendicular vectors, but the concept will be the same. Okay.
yes.
So suppose the rain is itself falling, let's say like this. So this is the velocity vector of the rain, and the person is, let's say, moving like this. So then we just have to use vector algebra to again calculate the difference of these two vectors. So it will become a more, in this case, the slant will appear to be even more because he is actually moving opposite the slant. But if he was moving in the same direction as the slant, then it would appear to be less inclined. In this case, the relative motion would be like this. So this angle of inclination is even more than the actual slant. But suppose the same, yeah. Now suppose the rain was slanted like this. And the person was walking or moving in such a way that is along the slant. Okay, then in that case, the rain would appear to be less slanted. It might even appear to be vertical in that case, in a special case. So all these different cases are possible, okay, and we'll discuss numerical examples, but it's all about vector algebra. Now the relative velocity of the rain in this case will appear to have an opposite slant than the actual velocity.
So if the man moves with such a high speed that the velocity of the rain will be in the horizontal direction,
That will have to be infinite then. But think about this now. For theta to 10 to 90 degrees, velocity of the man has to tend to infinity. No?
yes, sir.
So that is unlikely to happen. Okay.
Yes, sir.
Now, just one thing to understand about these type of questions, where we look at relative motion of rain with respect to a moving person. Raindrops have a very high amount of viscosity or drag force with respect to the atmospheric air through which they are cutting through. So raindrops don't experience only gravitational force, but they also experience drag force or air resistance or what is called viscosity. So raindrops in these type of problems are assumed to be moving with uniform velocity as they are coming closer to the surface of the earth because of very high drag forces. So that is why you might wonder why we are not taking acceleration into account in these type of questions. That, you know, while the person is seeing the rain droplets moving, they are in accelerated motion. The answer is that they are actually not in accelerated motion. They are moving with something called terminal velocity, which we'll study about later. But that happens because the air drag force or the resistance force, okay, that balances the gravitational force. That is an inherent assumption that we are taking while solving these type of problems. Okay. Okay, people. So hope this example was clear to all of you. So I will again send another worksheet for relative motion also. And there are a lot of good solved examples of relative motion in HC Verma, especially towards the end of the solved examples. So you can start going through them. There are problems based on relative motion of rain and moving person also. That is after the projectile motion questions, after 45. Okay. So now you can look to work out those questions. We are not done with all the concepts of relative motion yet. We still have to discuss one or two more important concepts and related problems. Okay. So if you get stuck in some advanced type of problem, don't get too worried about it. Plus this week, concentrate on doing the revision of projectile motion and 1D motion carefully because you have the test coming up. Okay. And don't forget to keep all the doubts collected for the doubt session that we have on Saturday, especially the doubts from the module HC Verma and the worksheets. Okay, we will discuss them in serial order. First kinematics and then anything else on Saturday's doubt session. Okay. That's it for today, people. Wish you all the best. Have a nice day.
Thank you, sir.
Thank you, sir.
Thank you, sir.